Pop's law, I have viscosity damping. Three things together. That three terms means mx1 double dot equal to k minus kx1 minus cx1 dot plus f. Now I have m larger than 0, c larger equal to 0, d larger equal to 0. And remember this. It's important. Because c cannot be negative. K cannot be negative. M cannot be negative. M cannot be 0 either. Because M equal to 0, that doesn't mean nothing. There is no system at all. Alright. In the first equation of motions, then I write again x1 dot equal to x2, mx2 dot equal to minus kx1 minus cx2 plus f. My matrix equation now is this. Rigid body motion, this is 0. That also 0. The vibrational motion, we have minus m inverse k, 0, with damping here, viscous damping, then we have minus m inverse c. And one more time. Oh, that's a big difference. Now, measurement equation got a big difference too. Displacement equation is okay. Velocity equation is the same thing. Then accelerations is minus m inverse k x1. We have another minus m inverse c k x2 plus m inverse f. I have displacement here, I have velocities here, I also have force here. I have three terms down in the measurement equation when you have acceleration measurement. Three terms. Let's come from this. If you have acceleration is here, this is the term, and that is becoming. Because I have state x1 and x2. x1 is state, x2 is state, but x2 dot. This is state, x1, x2. So this system only two states. What is the differences of this? See, we have spring here, but this one is the damping. If you add them together, then it won't vibrate forever, because it will stop. Because this guy will take the energy out. So this guy will be the one dissipate the energy. That's why. Your math. You understand? That's why. So mathematics, you just add one more term. But C cannot be negative. If C is negative, then it's not only vibrate, it's vibrate larger and larger and larger until spring broke. So this is why C has to be larger or equal than 0. C cannot be negative, K cannot be negative. Think about if this K is negative, then you've got a big trouble. So that's the damping. This matrix, if you solve eigenvalue here, you have not only frequencies, you also have damping. That means if you have C equals 0, this matrix, the eigenvalue will be pure imaginary. Pure imaginary means frequencies. The real power of the eigenvalue related to the damping. The imaginary power of eigenvalue related to frequencies. So That's the differential equations we're talking about. All right. So ideal spring, ideal damped spring, damped. Right? The damped spring means what? You have a damping involved in it. Spring and despot, like that. And this we call DMP. But in reality, all the spring got some sort of damping anyway. That's because the materials really got some damping. We can vibrate this forever. But in terms of the ideal case, yes, the spring you can vibrate forever. All right, that's a realistic case. Now, these few slides I added these few slides to tell you that all the system, doesn't matter what, all the combination of these three things, the whole system, nothing but only this, either rigid body motion, or vibration motion with damping. That's all. That's a real system. So these three motion is the basic. Now, if I look at the tube mass, all right. This is called tube mass damper. Tube mass means, for example, this represents the system. This represents the damping. For example, this M1 and K1 represent the 101. This represent the tube mass damper on the 86th floor. So that's the damper, and this is the system. If your system has only one frequencies, then I call just only represented by only one spring. But of course, the whole building won't be just only one frequency. Any building has multiple frequencies, maybe 1,000 different kind of frequencies. But if you look at that, this is the second order equation of motion, and this is the ordinary differential equation. So that's why last week that the Dr. Wang show you those. This is matrix equation. So you look at this, that's your matrix equation. Now, your matrix equation won't be 2 by 2 anymore. They are 4 by 4. And this matrix equation can grow to 100 by 100, 1,000 by 1,000, depending on how many degree of freedom of your system, depending on how many degree of freedom of your